alaikum. We in this week are going to look at finite difference schemes, the forward, the backward, and the average scheme. That's the Crank-Nocolson. We also are going to look at atomization and the stability analysis. These are the contents. First, we would like to look at the classification of differential equations. In physics, you usually get them in this form, where one of the coefficients may exist or is zero. I have to first clarify some things. So ux means del u by del x. So that means uxx is squared u by del x squared. And for example, uxy is del squared u by del x del y. So in this case, let's say u is some quantity. So the derivative of the quantity with respect to the second derivative, for example, second partial derivative. This is the mixed derivative xy, and this is in y, and this is in x alone, this is in y alone, and this is multiplication with some constant equals. So this, from this general representation, you can classify differential equations we often encounter in physics. How do we do that? We look at A, B, C. There is some mathematics behind this, but you end up with a discriminant, this. So D is b squared minus 4ac, and you're looking at the sign of D. So if D is greater than 0, you call it hyperbolic PDE. An example is the wave equation, for example. If D is less than 0, you can call it elliptic. And if D is equals to 0, you call it parabolic. Let's take one example. For example, let's take the case of elliptic. In the case of elliptic, when you go 2D, you have squared u by del x squared plus squared u by del y squared equals 0. Now, if we look at this, our equation, we see that this is second derivative with respect to x, which is here. So if you compare, then a is like 1. Let's move this guy a little bit so we can get to see. Good. Now what next? Do we have b? No. So b is 0 because we don't have any squared u by del x del y. We don't have that. And so b is 0. How about c? Yes, we have c. c is 1. So a is 1 for the Laplace equation, and c is 1 as well. So what do we say? We do d, which is b squared minus 4ac. However, if you look properly, b is 0, and therefore you have a situation like this: 0 minus 4ac. So a is 1 and c is 1. You have negative 4. Negative 4 falls under the category of elliptic equations, and that's how you do the classification. So you look at the equation, and then you look at the coefficients of these derivatives. For example, here you have alpha, and here you have 1. When you apply the same principle, you end up classifying it as a parabolic equation. And that's how you classify them. So for example, Laplace equation is elliptic based on that classification. Height equation is parabolic. Wave equation is hyperbolic. Now we move on to finite difference schemes. To do the finite difference schemes, we first have to look at the nature of approximation. If you are here, I, the next, your neighbor would be I plus 1, and your neighbor from the left would be I minus 1. So if you know the value ui, then you know the value ui plus 1, and you know the value ui minus 1. You can use these values to approximate u prime or u prime prime. So but if you are using 1, 2, 3 points, you call it a 3-point formula approximation. How about if you decided to use even more points to approximate? Let's say now you have even I plus 2. This is u I plus 2, and you go back here, you have I minus 2, so you have u of I minus 2. In this case you are using, so in this case you're using 1, 2, 3, 4, 5 points to approximate this. You can use it to approximate u prime, even higher order. For example, u prime prime prime. It's really important to note that u prime is also ux. For example, you're just doing the derivatives with respect to something. For example, if u is a function of x, you go u prime as ux, or u prime can also be ut or uy, depending on what you're looking at. Now, how do you estimate these values? How do you do the estimation? One of the methods is using Taylor series. So what do? If you want to use this method, let's call this dx and this dx. So if you want to use these three values, let's start with the 3-point formula. You want to use 1, 2, 3 nodes to approximate the function. You expand the function about here, and then you expand, or let me change color, about this line. Then you expand the function also about this edge, and then you add and see what you get. So the expansion is easy. So what we do is we apply Taylor series. So first we expand u from the right. So we do like xi plus delta x. It's like from here to here. So in Taylor series expansion, this is easy. It's ui plus delta x times ui. Like this is like du by dx, and this is delta x squared u prime prime, and then to the 6th, and on and on and on. If you expand also from here to here, that's this, you get these. I think this should be negative, not positive. Yeah, so you have plus negative, positive, negative, positive, negative. Now when you add these two equations, up and down, you get something like this. You get this plus this would be this plus this. I'm sorry I flipped there. So just know that u of xi plus delta x is as good as saying u of I plus 1. It's the same thing. And also u of xi minus delta x is as good as saying u of I minus 1. It's the same thing. Now when you add the two equations, you have the first, from the left hand side you have this, and from the right hand side this plus this will give you twice that, and this plus this will go, this plus this will be twice, would be 2 dx squared on 2, so this guy goes, and that's why you have this. This plus this, you get the idea. This and this will go, this will be twice, you divide by 2, you get 12, and that's how you go. And this will go, and the sixth order this will be there because the fifth will go. Now when you have this situation, you are in a position to estimate this because this is your target. So how do you do that? You first try to relieve it from this guy, so divide by dx squared, dx squared, dx squared, and that's what you see here. And these guys, so when you divide this by dx squared, this guy would become like this. When you divide this by x squared, it becomes of order 4. Now this is error, and this is also error. To realize the error, you have to add these two guys. But it's just saying it's as good. Let's say the error is 2 or 0.2, for example. Now if you do 0.2 squared plus, let's say ui is here, and then 0.2 to the fourth order, this is very small compared to this, and therefore we usually discard the higher order errors, because if you are dealing with small numbers, if you square them, they become smaller. And this is why we discard the first one, we discard this one, and we take this as the highest order of the error. And therefore the truncation error is of order 2. So is to dx squared accurate. That's what it's trying to tell you. This is the 3-point formula for estimating second order derivative. You can also target the first order derivative and apply these methods. In the appendix section of this file, you inshallah will find lots of derivations like this one. So how do you, now let's say you are looking at 5 points. This is I, this is I plus 1, this is I plus 2, this is I minus 1, this is I minus 2. How do you approximate, for example, f prime of x, or, okay, I don't want to confuse you, let's go here, let's say u prime or u prime prime. How do you approximate that? Like we did, you expand the Taylor series along this side, expand the Taylor series along this side, and then you add or subtract depending on the target, if you're looking for this guy or this guy. However, it is not that easy as said. So what you should do is, first, let's assume I'm looking at u prime prime. I have to approximate this is the technique, as some a times u of I minus 2 plus b times u of I minus 1 plus c times u of I plus d times u of I plus 1 and plus e times u of I plus 2. So I'm approximating the derivative using these points. At this I cannot expand, no expansion, but I can expand here, expand here, expand here, expand here. And when I expand, so that means I'm going to expand u of I minus 2 using Taylor series. You also expand this using Taylor series, expand this. No, you cannot expand this, because that is the point from which you refer to. You expand this, you expand this, and in the end you are going to get the constants. So you're going to do the matching, and then you get the constants a, b, c, d, e, and from there you now find the final form of u prime prime. And the process is easy. The only heavy part is the algebra, but you guys are already good in numerical analysis and solving system of equations, because you're going to have system of equations and you're going to solve for these equations to find a, b, c, d, e, and the final form would look like this. So maybe the a was with this guy, and the b was with this guy, and the c was with this guy, and the d was with this guy, and the e was with this guy. And that's how the point formula would emerge. Do not forget, if you are looking at these schemes, it depends on where you are going to. Forgot to explain this. You have done this with Dr. Isama, I'm very sure. But if you are here, if you are at I, you're going to use only I plus 1, then this is a forward scheme. However, if you are here and you're going to use I minus 1, this is a backward scheme. And if you are in the middle, you want to use these points, that's called central scheme. And the ones we demonstrated here for the 3-point formula and the 5-point formula, they are all central schemes, as you can see. That's why when we expanded to the left and to the right. In forward or backward schemes, for example, if you take the forward scheme, f prime of x equals f of x, u prime equals u of I plus 1 minus u of I over, let's say, dx, for example. This is a forward scheme, right? Then you can also have the backward scheme where you can, this is for the first derivative, and on, for example. Or you can have the backward scheme where you can go to the back. U prime equals u of I minus u of I minus 1 over dx. All these things. Anyways, let's keep going. So you are going to have the point formula for second derivative as this, u prime prime. What does this mean? It means if you have an equation, let's say you have d squared u by del x squared equals 0. Let's say you're solving this Laplace equation. You can choose a grid with 5 points, so that at any point I, you can go I plus 1, I plus 2, I minus 1, I minus 2 to estimate this second derivative. So that is, you are going to say I'm going to take the u of I plus 2 with u of I itself, and another u of I, sorry, with u of I plus 1. So you see plus 2 plus 1, then I, then minus 1 minus 2. It's like exactly taking the points. So I minus 2, which is this point, I minus 1, which is this point, then I, which is this point, and then I plus 1, which is this point, and I plus 2, which is this point. That means I want to approximate u of second derivative. I am doing the second derivative because that's what we will be mostly using in this course. But the first derivative is already easy. You already have taken this one. Now, yeah, okay, so the time derivative as well. For the time derivative, it's usually easy. So what do? We expand, because time moves forward. That's why it's easy. Time moves forward, right? And because time moves forward, what do? So if this is t, you can I don't never seen t minus 1. Okay, yeah, okay. In simulation, you can also go. Sorry. So how do I? We use n for t. Let me draw it properly. So this is n. This is n plus 1. This is n minus 1. But if you're dealing with t, you want to move forward. Anyways, you can still move backwards, but time moves forward. So people naturally tend to use forward derivative for time. And another thing is we use the forward difference. That's it. So we expand from n to n plus 1 if this is dt. So we expand the Taylor series around this point, and that's like u of n plus 1 equals u of n plus delta t u prime, but this prime is for t, that's why you have ut here, plus delta t squared on 2 factorial u t, that's double derivative, plus order 3. You can keep going on and on, but like I said, this is also, in this case, this is an error. This is also an error because we are going to truncate here. So usually in Taylor series, the last term you want to stop at, if you are stopping at here, then you consider these guys errors. If you wanted to also include this, then this guy will be the only error. If you wanted to include all of these terms, then the next guy will be the error. That's how it usually works. Because the maximum error is the last term you stopped at. Why is that? Because, like I said, if the error is, let's say the error is 0.02, now the last, let's say we stopped at order 4. So the next term would be order 5. If you do 0.02 to the fifth order, you are going to have even smaller value. So it's like you don't even want to be including those small values. because they're not going to affect much. Their effect might not be significant in regards to the simulation accuracy. All right, yeah, and that's it. So we expand up to this level, but then we are interested in u prime, and u prime is this guy. So we have to relieve this guy from the dt, and therefore we divide this by dt, divide this by dt, divide everybody by dt, and you end up with this. Yeah, let's get rid of this so you can see it properly. You end up with this. Like I said, these guys are errors, but this guy is the highest order, because the order of dt is better than the order of dt squared. I mean, it's bigger, and so the temporal accuracy is of the order delta t, and that's it. Now let's apply this finite difference schemes to heat equation. Now heat equation, the heat equation is parabolic. How do we know that? Okay, so this is the heat equation. Let's do some heat equation thing here. This is the heat equation in 1D, for example. So it's du dt equals alpha del squared u by del t squared. So we're looking at we're looking at, yeah, the d is b squared minus 4 ac. Now going by our method, a should be next to the second derivative. Oh, sorry, this is x squared. Sorry, a should be the guy next to del squared u by del x squared, and clearly here a is alpha. A is this guy. Good. How about b? B is supposed to be next to del squared u by del x del y, and we don't have this term, so b is 0. So b is 0. C is supposed to be next to del squared u by del y squared. Clearly there is none of that in this equation, so c is 0. And what are you left with? 0 minus 4 times a times 0. So the heat equation is parabolic, just so you know that. Now let's move on to how we can discretize the heat equation. Okay, so what did we do? Let's do it here. So we have del u by del t equals alpha del squared u by del x squared. First thing you would like to do is, this is a derivative with time, and this is space. So the first scheme we would like to implement is called the forward time scheme. So we're going to apply the forward difference for this. So this would go like u of I plus 1. So you're going to, if this is I and this is I plus 1, no, we're not looking at I. Let's even give them, because we have t and x. So let's make u for t n, for x I, and therefore for the time, if you are at n and this is n plus 1, you're going to use a forward scheme. So how do? You can say u of n plus 1 I, because I is not changing. When time is changing, because they will change independently, right? Minus ui of n, because you're going to do this minus this, right, over delta t. That is forward time. So you're going from here to here. You're approximating forward. And for the distance, we do central. Let's use the central 3-point formula. Central, for now we will use the central 3-point formula, but you can also use the 5-point formula. Central space. How do we work with the central space? You go like u of, so now we have to be careful, because n is for time, I is for space. So u n of I plus 1 minus 2 u n of I plus u of I minus 1 n. We divide this by delta t squared. This is exactly the scheme we used. Let's find okay, so this is the forward time we used, as you can see, this one. And for the space, where is this 3-point formula? Yeah, for the space we used this, right? So we just plugged them in. That's what we did. Yeah, so we plugged them in. And this is called, oh, there is alpha here. So I'm gonna get this alpha. But let's put alpha. This scheme is called forward time central space scheme, and that's it. So in this scheme, what do? You are going to have something like this. Yeah, so that's exactly what we have here. And then you want to go to the next. So in this scheme, you are all about next depends on previous. That's all. So so which one is next, which one is previous, and which next are we talking about? Is it the next in time or the next in space? It turns out that you want to first loop in time. You want to first loop in space and then later loop in time. This is how it goes. Time, then you loop all over space. Then you increment time. Then you loop all over space. Then you increment time. Then you loop all over space. And that's how the algorithm works. So this means I will be looking at un plus 1 as my next. Not so at each un plus 1, I am going through the ui's, that is the space. So we will see this, inshallah. Now let's go back here. And in this regard, we are going to make this solve for this in this equation. So how do we solve for that? First dt will jump here, and then when dt jumps here, you have, let's do it here. What do we do? Squeeze these guys in, squeeze these guys somewhere like here, and let's solve for u. So ui of n plus 1 is going to be dt. First I'll take this guy, so it's ui of n plus dt times alpha over, here is supposed to be dx, please. dx squared. I hope I did not mix, yeah, sometimes the dt, yeah. So by dx squared, then into ui plus 1n minus 2 ui n plus ui minus 1 n. That's it. So here you have all the un's, and then here you have u n plus 1. These guys have i's, and this guy has I, but these guys are in the past, while this guy is now. And that is how the forward time central space algorithm works. So you are going to at each now loop through what you got in the past to approximate the now. That's how it works. Okay, so someone might say, when we come to code, inshallah, we will see how to implement this better. Now let's move on to the error. Yeah, so how is the error? If you could remember, the error of estimating time derivative is of order dt, and the error of this guy is of order dx squared, because when we truncated the Taylor series. So then the error at each time step, when you do when the computer make estimation, it is going to make this error in time and this error in space. And that's exactly what I wrote here. So the local truncation error. Why do we call it local? Because it happens at each iteration, right? So it's like the summation of the two. Okay. Now how about the backward time central space? I want you to have a look at the forward time central space properly before we go to the backward time central space. Time moves forward, so we go to n plus 1. But so that means we have a situation like this. This is n, this is n plus 1 in t domain. This is the delta t. But if you want, you can change this to the backward time. How does it work? But you know that you cannot go back in time, and this is why the backward time is different from the forward time, because in the backward time you cannot solve the now using the yesterday, because already you have compromised the yesterday. So you have a situation like this. This is n minus 1, this is n. You're going back. So we said the heat equation is like this, for example. Now, to go back in time, you have to say ui of n minus ui of n minus 1 over delta t equals, then you are now going to use your central space. So this is backward in time. Back time. However, here you can maintain your central space. So u n I plus 1 minus 2 u I n plus u I minus 1 n. But we have a situation here. We know we cannot go backward in time. So what do? So we do something like, we say let n equals n plus 1. And therefore, we now rewrite this equation so that n is moving forward. So that means so we're now going to pretend that we are using the now to estimate the future. Yeah, so that means we're not going to use the now to estimate. So when you make n plus 1 here, this one becomes, let's get rid of this, u of n plus 1 I minus, this one becomes n plus 1 minus 1, it will become un over delta t equals alpha. Oh yeah, here I forgot we have dx squared. Alpha on dx squared into u. Here will become n plus 1 I plus 1 minus 2 u I of n plus 1 plus u I minus 1 of n plus 1. So what you have here is the backward in time scheme. So this is the, it's called the B, backward time central space, because this is the back, like we say. This is the back and this is the central. In this case, you cannot solve for, it's really difficult in this case. What you have to do is you have to do some kind of cooking. Okay, let's first go back here. You see, here we are able in the forward time central space. Here we are able to estimate ui at n plus 1 using all the ui's. So we are estimating the now from the past. However, here it is not possible because we are having a kind of tomorrow and today, and therefore what we do is we call this implicit. What do you do in implicit? It's like cooking. So here you add the recipes one by one. So you add the recipes one by one. That's explicit. After this, then you go this, and but here you are going to solve at once. So you cook, you put everything, and then you cook it. So that's how I understand this. So this is called implicit scheme, backward time central space. And this is what you got. You got the backward time central space discretization. What do you do with this? You want to, because you have okay, this guy is n plus 1, this guy is n plus 1, this guy is n plus 1, n plus 1. You want all the n's in one side and all the n plus 1's in one side, at least. So to do that, you rewrite this equation. For example, this guy, first dt will go there. You have a situation like this, ui of n plus 1 equals, this guy will go there. Oh no, because this ui of n will be the one to stay, right? So all of these guys will be there. So you have ui plus 1 of n plus 1, but this, so you can just let some value lambda be alpha, because dt will go up here. You have like dt over alpha, and then you have this dx squared come here. So alpha dt by dx squared. So you don't have to write them all the time. So let them be there. So you have here lambda will multiply this guy, right? and then minus lambda multiplying this guy again. But don't forget, this is ui, and we are bringing this guy to meet him. And to do that, so this one, which is this, is what you see here. Of course, the negative has run. Okay, what do I do now? Let's multiply both sides by negative, so you can see. So this will be negative. So these guys will be. Why don't we just, anyways? I trust you understand what I'm doing. It's just trying to solve for this guy, and then making this guy go here, but we have to get rid of the negative, and the negative will affect those guys, and that's why this term, this very term, will be now negative, like this. And then this 2 is going to meet with this guy, but this guy now is, when they meet, you have, because they eventually will be positive when you multiply by a negative, you have this term. And the final one is, yeah, okay, so I mistakenly switched between this guy and this guy, but anyways, you get the idea, because the lambda is going to multiply this and this and this, but then when this guy comes over, he meets only this guy, so this guy is there, this guy is there with the lambda, and then you have all these terms. With this one, with the plus, that's this one. Sorry, I've been focusing on this guy to be this, but no, this is this, and then this guy. Let me clean this. This guy is this guy. You successfully have covered all the okay, I'll make it clean so you can see. Let me delete everything. Yeah, so you have successfully isolated this guy, which is here, and everything is on the left or on the right, depending on how you see it. So what do we see here? We see a situation where you have at n, you are going to have n plus 1, n plus 1, n plus 1. We know it is not possible. We can only estimate n plus 1 using n. So we are going to have a matrix like this. Let me show you how the matrix is going to be. Let's say this is let's what do I do? Okay, so I'll go to another page and show you. Let me open up another page here and show you what's going on. So we have, let's get here. We have u of I n equals minus lambda u of I plus 1 n plus 1 plus u I n plus 1 into 1 plus 2 lambda minus lambda again u of I minus 1 n plus 1. Okay, so we are going to look at this. This is, let's say we are in 1D. This is a rod. Don't forget, we're solving heat equation. This is for heat equation. Let me write it here. The reason why I'm very slow is because it's a new concept. We have to be slow for you to digest, and I'm not very good in making short videos. Anyways, let's say these are the, you discretized it into, but in the end you have boundary conditions. You have A, you have B. So you have A, you have B. Now you are going to start and you have this equation. You're going to start, so this one will be U0, U1, U2, U3, U4, U5, U6, and this is the last U. We can call it U. Let's call this UK minus 1 and UK. Or I would say, okay, let's call it, yeah, let's call this UK. So what do we do? At every point, because we are using 3-point formula, if you are here, you need 3 points. It is not possible. So you can only have 3 points from here. You go here and here. And when you are here, and when you are here, you can go here and here, right? And when you are here, you can go here and here. And when you are here, you go here and here. And when you are here, you cannot go there. So you can only be, when you are here, you go here and here. And that's how you are going to iterate. And with this, we can now write our equations. So what do we see here? But this is usually the boundary condition, and it is known. U0 is usually the boundary condition. Don't forget U0n. Let me not confuse, because there is initial condition as well, and there is boundary condition, right? Initial condition is for n. Boundary condition is for I, right? And this guy is known as well. Usually they are known. So you are only going to find these guys. These are the unknowns. And how do you get that? You are going to write the equations. Let me first get this equation so you don't get confused. I'll copy this. Copy. All this is happening, all these things that you see will happen at UN. Then at UN plus 1 again, you have the same process. Copy, paste. At UN plus 1, you are going to have the same process. And then at UN plus 2 until you reach the last U in time. So UN plus 1 I, UN plus, UN I, UN plus 1 I. And let's squeeze this. And I hope you understand the operations. The UNs are iterations in time because N is for time. N is for time and I is for space. So I can run from 1 until K, and N can run until 1 until maybe big N. That's what we're trying to do here. So you see, if you have, now let's write the equations, because these dots that I am giving you are equations. So how are these equations going to be? Let's write them. Let me zoom in here and start working on them. So the first case is you have, oh, I think I copied something which I wanted to paste. No, not this one. There is this one that I copied, which I wanted to. Copy. You have to bear with me because the video is really long, but it is what it is. Okay, trying to, okay, this is too long. What's making it this long? Trying to, that, oh, that's the maximum I can zoom. Okay, fine, I'll get this up here. Now we are going to start this is 1, this is 2, this is 3, this is 4. I mean, I equals to 1. Let's say I equals to 1, I equals to 2, I at the iteration I equals to 4, and until you reach the end. So let's start with this. So I, or we can call it UN1 equals, so I equals to 1 now, equals minus lambda U. Okay, I wish I would have the other one, the minus 1, come here, and then anyways, it's fine. UI2 n plus 1 plus U1 n plus 1 into 1 plus 2 lambda plus, oh yeah, no, minus lambda U I, or 1 minus 1 is 0, U0 n plus 1. This is the boundary condition. This is this edge, like I told you. This is this edge, U0, and it is known. So it's a number. So what do? We move it to, yeah, we can leave it for now, but it's better we move it to the left hand side. So you have U1n. This happens only for the first row and the last row, plus lambda U0 n plus 1 equals minus lambda, oh, I mistakenly here, I'm supposed to write U minus lambda, yeah, minus lambda U2 n plus 1 plus U1 of n plus 1 plus 2 lambda, let's say plus 0, because we've taken the other guy. Now how about, so this is first, how about U2? U2, we're going to put 2 here, so U2n equals minus lambda U2 plus 1 is 3 n plus 1 plus U2 n plus 1 into 1 plus 2 lambda minus lambda U1 n plus 1. We're just following this protocol. How about U3? U3 n equals minus lambda U4 n plus 1 plus U3 n plus 1 into 1 plus 2 lambda minus lambda U2 n plus 1. What do you notice? A sequence. Da, 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 until UK minus 1 n. UK minus 1 n is this guy, right? It's this guy. Okay. So what do you notice here? If you are here, U2, you're going to take U3, U1, right? If you're at U2. And that's what happened. You see, you take 3, 2, 1. Because you are in the second ranking. You are at I equals to 2, for example. And that's what is happening. Now UK, but UK will have okay, let's write it first. Is minus lambda U to the, so U to the k. because when you do k plus 1 is k, n plus 1, then plus uk, because it's k minus 1, it's supposed to be k minus 2, right? Yeah, because if you let k minus 1, if you let I equals k minus 1, so here it's going to be uk, and here is going to be k minus 1, and here is going to be k minus 2. So uk, and then which one was I having here? So the plus 1 is going to be uk, k minus 1, n plus 1 into 1 plus 2 lambda, then minus lambda u k minus 2 n plus 1 and that's it. So now we have these results. So why don't we put them in matrices? We can put them in matrices this way, but before we go there, we will see that uk minus 2 is this, and uk minus 1 is this, and uk is that. So because we know this is known. I forgot to tell you, there are two types of boundary conditions. Yeah, there are three types. I mean, there are many boundary conditions, but the most popular ones are the Neumann. This is U. They call it Neumann, the English people, and the Dirichlet. This one gives you du by dx at the boundaries, or d squared u by dx squared. The Dirichlet would give you u at the boundaries, u of a, u of b, depending on what you get. We'll look at implementing boundary conditions here, but in this discretization, because we are assuming this value is known and this value is known, so we are using the Dirichlet boundary condition. It's just telling you that maybe u of a is 0. Sorry, u of b is 0. U of a is 2, for example. That's all. And this is why we say they are known. So you cannot involve them in the discretization. And if you look at because this is uk is known, and therefore the term with uk, which is this guy, has to go to the next. So what do you notice? The first and the last. In the last, we want to do something like this: plus, then equals. Good, because this is known. And that's how you condense it. This will become a matrix like this. You will have a matrix like this. How do I do this? So equals, so let's, I already have destroyed but anyways, I hope you understand, inshallah. It becomes a matrix like this. These guys, you have this guy until this guy. So you have u1n plus lambda. So you have u1n plus lambda, u0 n plus 1. You keep going until you have u so where yes uk minus 1 uk minus 1 n plus lambda uk n plus 1, because they are known, equals, so you're done with these guys. Now these guys, what do you notice? Look at this. You have u2, u1, 0, u0, and then u3, u2, u1 plus 0, u0, u4, u3, u2 plus 0, u1 plus 0, u0, and on and on and on. And you end up with a matrix like this. First, let's get these guys. un plus 1, sorry, u1 of n plus 1, u2 of n plus 1, until uk minus 1 of n plus 1. And what is in this matrix? Of course, you have, because u0 is gone, it's not there. So you have a situation like this. This is u1, then u2, right? And then u2, u3, u1. We rearrange them usually, because to be able to get this, I assume everybody watching this video is familiar with linear algebra, so you already understand how to arrange matrices if they're supposed to multiply. And what do you get? You get this u1, this is the coefficient, and u2. So I ignored u0 because u0 is not there. u0 is not always there, so you can ignore u0. And then the coefficient of u1 is this, the coefficient of u2 is this, so you have the coefficient of u1, 1 plus 2 lambda, and then the coefficient of u2 is minus lambda, and that's it. So u3, u4, they all don't have any coefficient. When you come to the second row, we have u3, u2, u1, so everybody is there, right? So you can put the coefficient of u1, which is minus lambda, and 1 plus 2 lambda, coefficient of u2, and coefficient of u3, let u3 be somewhere here, minus lambda. And that's how you go until the last one. So what happened in the last? In the last you have only uk minus 1, and that's this guy. This guy has a coefficient, which is 1 plus 2 lambda. uk minus 2, that this guy has a coefficient, minus lambda, and that's it. There's no other coefficient, so zeros follow. So this is the matrix you get. So you have a situation like this. This is a x equals b. The principles of linear algebra give you that to get x, you have to do a inverse times b. So at each time step, you must solve matrix equation. And this is why it is called implicit. You're trying to find these guys, and that's a summary of so what you see is at u, for example, at un, you have to solve ax equals b. at un plus 1, this one, you have to solve it. So you solve at here, you solve at here, and you keep solving at different time steps. So what do we see? We see the difference between implicit and explicit scheme. This is an implicit scheme because it takes everything together and solve it. What is the explicit scheme saying? Let's go back in here. The explicit scheme, so this is the reason why we say you have to solve this kind of equation here. And the error, as usual, because you already know the error. There is the Crank-Nocolson scheme. What does this scheme say? It says, oh, how about, you know that f prime prime, oh no, sorry, u prime prime is for the forward FCTS, for the FCTS, sorry, forward time central space plus the backward time central space, you take the average. That's all it says. It says you can make them as an average. What is this trying to say? It's trying to say if you're solving the equation, let the left hand side, because the heat equation is like this, dt by, sorry, du by dt equals alpha u squared du by dx squared. So it says if you are solving this, why don't you leave this as it is, but you can use, in this case, the backward, and then for this one you take the average of the schemes, and that's what you're going to do. You're going to take the average, and then you end up with something like ui n plus 1 minus ui n divided by delta t equals a half. Okay, you already have alpha over 2 dx squared into what? Into ui plus 1 n plus 1 minus 2 ui n plus 1, that's the backward, plus ui minus 1 n plus 1. So this one is in big bracket, plus, because you've taken the average, plus uni plus 1 minus 2 ui n plus ui minus 1 n. And that's just it. And in this case, you're going to apply the same principles. You isolate the n's in one side and the n plus 1's in one side, and yeah, and that's it. So this is the Crank-Nocolson scheme, and when you do the isolation, you find all the n plus 1's here and the n's here. I believe now you know what lambda is, you know why we isolate them. You are the same in the same way, because this is also an implicit scheme. Why? You have to solve ax equals to b. That's why it took time for me to explain this, the backward scheme. So there's something you need to understand. So the forward time central space scheme, this is good, but has stability issues. The backward time central space framework is very expensive. You have seen it's very expensive. You have to solve ax plus b many times, which is really difficult. So it's expensive, but unconditionally stable. And also the same goes for the Crank-Nocolson. Don't forget the Crank-Nocolson is just the average. It's just backward time and average of the backward and the forward schemes. That's what I want to draw your attention to. And that's it. So it achieves this. It's unconditionally stable for heat equation. These schemes in the future we will see they break down at some points. I already explained to you. If you have, now let's look at boundary conditions. If you have the Dirichlet, you will be given u of a equals to something. Oh no, we cannot use x here. You can use, no, you cannot use k. Anyways, u of a equals to f, and u of b equals to g, and that's it. So in your iteration, you are going to set u of a as f and u of b as. If you have a Neumann boundary condition, if you have du by dx equals f, so this is trying to tell you you can use forward difference, backward difference, any difference. But the best for you can say, okay, I'll take ui forward scheme, ui plus 1 minus, so uin, so minus uin over dx, for example, equals f. And then I can say now that because now you're looking at the boundaries. So the boundary, let's say du dx at x equals to a, for example. So if at x equals to a, and this is, let's say we're solving for and this is the a and this is the b, so you're given the du df at this point equals to, sorry, du dx at this point equals to some f, and therefore you now have to say, so it's about u0 and u1, right? Because the far edge one is u0, like we saw in the example. So it's about this. So you can now say that I can take this guy up here. I can say u1 n equals dx times f plus u0 n, and you put it in the algorithm. That's all in the structure of your equation. If you have Neumann boundary condition, all you have to do, if it is at some point maybe c, you go to that point, you apply this. But there is, what we show in the note is a 3-point formula. So the 3-point formula for boundary condition is like, okay, this is 0 1 2, so u0 u1 n n u2 n, and therefore you, like I told you, how to find the 3-point formula is easy. You just find it. But anyways, it's going to come like this, then you equate it to some value which you are given. It's really easy. You don't have any headache. Now let's look at the stability analysis. This is really important. Remember I told you that the forward time central space scheme has stability issues. So what is stability? Stability is if you are trying to solve the equation, this scheme may give you wrong values, or errors can accumulate, or you can have technical problem. That's stability. Stability is, let's say I'm solving and I expect the graph to look like this, but when I use the FCT scheme, I get some unstable bump. Everything is correct, but I get this. So this guy, if I was using this guy, I have to check for the stability so I don't miss out, because in most cases you are solving equations, especially in research, you are solving equations and you don't even have any idea how the solutions should look like. You don't have a benchmark, and in such cases you need stability, because if you are supposed to get this curve and you end up with this curve, for example, you are screwed up. And so how do we detect stability issues? How do we manage stability issues? There is this guy called Neumann. You see, the spelling of this guy's name is really difficult. All right, they call it Neumann. I call it Neumann. Anyways, because the guy is not here, whatever you call the name, it's fine. So this man says, why don't we apply a trial solution to the scheme, to the FTCS scheme? So apply this solution and see what will G be. G is target. What would G need to be for the equation to be stable? That's all you need to know for now. Now let's look at it. Okay, so you get this ansat, right? Call it ansat. And do you remember we have our for the heat equation, is du dt equals alpha squared u by del x squared. Then you remember we said this is u n plus 1 I minus u I n over dt for this guy, and then for this guy equals, we said alpha, and then we said u n plus 1 I minus 2 u n, no, there was no n plus 1 here, there's I plus 1, right? And then I, and then plus u n of I minus 1 over dx squared. And then we said, and then we let lambda equals dt times alpha by dx squared, so we don't have to write, so we can get this guy and this guy and this guy together, we call them one value lambda, and you end up with the value like this. Where is it? Okay, so we don't have it, I'll write it here, and you end up with a value like this, like u n plus 1 I equals u I n plus lambda into u of I plus 1 n minus 2 u of I n plus u of I minus 1 n. That's what we get. So what will happen if we used, if we assume that u is this? So how do we write u of n plus 1? So u of n plus 1 I would be, just make n plus 1. Wherever you see n plus 1, n, make it n plus 1. So it's like g n plus 1 exponential I k xi. How about un, but I plus 1? So it's the same thing. So you are going to have u I plus 1 n. So we, wherever we see I, make it I plus 1. So it's like g n exponential I k x, right, plus, okay, I can write I plus 1, but xi plus 1 is like delta x, x plus delta x, or you can call this g n exponential I k x plus delta x, like this. Now when you do this, you end up with a situation like this. So instead of this, you have this. Instead of this, you have this. You get the idea. And instead of this, you have this. Instead of this, you have this. Instead of this, you have this. So what happens? You can factor out the g, because g will be common, but this is gn plus 1. You can divide both sides by gn. And you have only one gn here. You can also get rid of all exponential xi's. And because this is exponential, this is like exponential ik into x minus delta x, which is going to give you exponential ikx minus exponential ik delta x. So this ik delta x will be the one that remains. The ik will go. So as for this one. And what do you end up with? You end up with a situation like this. So you need to recover some identity from trigonometry. Exponential I theta, right, plus exponential minus I theta over 2 is cos theta. I hope you can remember this. And that's exactly what happened. So this guy and this guy, so if you have this guy and this guy, you multiply them by 2. So if you multiply this by 2, it's the same, right? It's the same. So when you multiply them by 2, you have this 2 is there, and these guys will become 2 cos k dx. That's it. And then you factor out the 2, and then you have what you have here. And because you have what you have here, so 1 minus cos kx, if you use the identity again, so 1 minus cosine theta is sine squared theta over 2. How did we get here? If you remember this trigonometric identity, I hope I can remember. Sine A sine B plus cos A cos B. I think we're going to, yeah, okay, so let's write them first. Sine A, sine B, no, yeah, okay. Sine A plus B, let's do it this way. Sine A plus B cosine A cos B plus cos A sine B. Then sine A minus B, for example, is sine A cos B minus cos A sine B. And then cosine A plus B is cosine A cosine B. Oh, yeah, I'm mixing the B's, right? This is B. Cosine B plus sine A sine B. And then cosine A minus B is cosine A cosine B minus sine A sine B. Yeah, I think we are going to use these guys. So just set A equals to B and subtract. This equation 2, this equation 3, and subtract. if you set A equals to B here and subtract, you end up with that relationship, this relationship. Yeah. Okay, so the essence, if you did not forget, we're looking at G. So this is G. Let's get rid of this guy. So this is G. What is the maximum value G can get? The maximum value G can get is what? Because when you say 1 minus 4 lambda sine squared whatever, we know that sine theta behaves from 1 to minus 1, and we see that we are having 1 minus something. So for G to be positive, we require G not to be more than 1. So G has to be, there's a long story behind this, because this G, it's the amplitude of a Fourier mode, because when Neumann analysis is all about approximating the initial conditions as a Fourier mode, but we don't want to get into that because it's a long story. For now, we require G to be less than or equals to 1, and to achieve this, the maximum you can get is when you set lambda to a maximum of 0.5 or a half. That's the condition. And therefore, if we set lambda to a maximum of this, then the stability criteria would yield, because lambda is, we already defined lambda as alpha delta t over the delta x squared. So we want this value to be less than a half all the time in order for this condition to be valid, because the heat equation is diffusive and highly smoothing, so it does not support on-physical oscillations or a runaway growth, say for example. So the lambda equals 0.5 ensures that the amplification of this G is between minus 1 and 1, correctly modeling the diffusion process. And that's exactly what the analysis is. So we require that lambda equals this. This is also called the CFL criteria. When we solve for diffusion equations, you get this. For different equations, for example, for the wave equation, we have another, I'll show you in a minute. For the wave equation, we have this, when you do the same analysis we just did. For the advection equation, you have this. And this is for our diffusion equation. So we will discuss more about this when we come to apply it, inshallah, in real time in class. Let's see what more. Yeah, we already, I think these are the most important things I would like you to know. Fortunately, it's a very long lesson, but alhamdulillah, we have arrived 1 hour 35 minutes. So in a nutshell, the 4 times scheme is explicit and it has conditional stability. We have to have lambda less than or equals to 0.5. The temporal order is of order t, and the spatial also of order dt and order dx squared. And the backward time central space is implicit, it's unconditionally stable, and these are the errors. The Crank-Nocolson is implicit, unconditionally stable, these are the errors. What are the advantages? This is cheap to calculate. It doesn't take time to see the results. These guys are expensive because you have to wait a little longer to see your results when you run these schemes. This has stability issue, this has unconditional stability. So alhamdulillah, if you go through the material, you will see I've made some derivations, and you'll be good with that, inshallah. Yeah, so you see lots of things here. These are just derivation, just for better understanding.